Dr. David Montgomery, so please grab your final cup of coffee before lunch and take a seat. As you're taking a seat, I wanted to do a brief shout out regarding the Cropland Grazing Exchange. It's a program with the Minnesota Department of Agriculture, and it actually helps match livestock producers who need cropland or pasture land to graze with people like Jerry, who don't have livestock, but who see the benefits of livestock as a combination with cover crops. So Kelly Anderson with the Department of Agriculture is here. She can talk more about it.
Thank you.
And we have little brochures on the Ag Department table and also on the SFA table. And I'm sorry if I'm shouting, I feel like I am. I also wanted to introduce Paula Sunday. Paula, stand up. Paula is a representative with Senator Tina Smith, and Senator Smith is part of the Ag Committee in the U.S. Senate, and we are pleased to have a representative from our congressional delegation here. Thanks for being here, Paula. Being from New Ulm, I come to St. Peter a lot, and I actually come here to do what I call my big shopping at the St. Peter Food Co-op. And I did just want to draw your attention to a few of the items in and around St. Peter in your program and on campus. Jason shared some information about St. Peter and about Gustavus Adolphus College. So before you leave town, you might want to check out a few of the things that are in your program. And if you want supper, grab some from the takeout at the St. Peter Food Co-op. It's delicious food. Okay, membership in SFA. A number of you I know are SFA members, and I want to thank you for that because our membership is the backbone of our farmer-to-farmer network. Membership dues are $40 for an individual and $50 for a family. We have a $75 category, $150 business membership. And membership enables you to get into conferences like this at a lower cost. It also puts you on our e-newsletter Connect mailing list, and it really enables us to keep our farmer-to-farmer network thriving. I'm not a farmer. I consider myself a food advocate and someone who really cares about the environment, and I didn't think twice about joining SFA before I started working for SFA. So I really encourage anyone who's not a member to join. The membership sign-up table's outside. Jason can take membership, and we can accept membership by credit card. We have a monthly giving program, and we can take cash and checks as well. Without further ado, I would like to introduce our keynote speaker, Dr. David Montgomery. I first heard Dr. Montgomery a couple of years ago at a pollinator conference and was really amazed at his presentation. And he was recently a speaker and major program partner at the Nobel Conference on Soil Health here at Gustavus last fall. Dr. Montgomery is a MacArthur Fellow and a Professor of Geomorphology at the University of Washington. He is an internationally recognized geologist who studies landscape evolution and the effects of geological processes on ecological systems and human societies. An author of award-winning popular science books, and I'm just going to hold these up because they are for sale out in the vestibule. This one is The Hidden Half of Nature, and I believe that had just come out a couple of years ago. And your most recent, Growing a Revolution. And he has hard copy and soft cover, I believe. Just soft cover. Dr. Montgomery has been featured in documentary films, network and cable news, and on a wide variety of TV and radio programs, including Nova, PBS NewsHour, Fox and Friends, and All Things Considered. His books have been translated into 9 languages, and he lives in Seattle with his wife Ann Bickley and their black lab guide dog, Dropout, Loki. Hope I'm saying that right. Connect with him on digtogrow.com or follow him on Twitter at digtogrow. Please join me in welcoming Dr. David Montgomery.
Thank you. It's a pleasure to be back in Minnesota, although the sun did come out briefly last week in Seattle, so I had slight trepidations looking at the weather forecast coming here, but all is good. By way of confession, I'm a geologist. I'm not a farmer, I'm not a biologist, I'm not a botanist. What I want to do is to try and explain to you over the next 50 minutes or so why a geologist like myself would spend a whole lot of time, a whole lot of nights and weekends for the last 10 years writing the 3 books that are up on the screen. It's what Ann, my wife, and I lovingly call our Dirt Trilogy after that first book. And that first book, Dirt, the Erosion of Civilizations, is the one you might expect a geologist to have written. It looks backwards through history, and the one-sentence summary of it is essentially it's a look at how societies in the past that did not take care of their land, which it turns out was most societies in the past, actually shortened their own longevity as civilizations by not taking care of their soil. That middle book is the one that Ann and I wrote together. She's a biologist. And it focuses on the sort of new understanding of microbial life, of the life in the soil, the invisible part of nature, we call the hidden half of nature, and how it interfaces, the new thinking about how it interfaces with plants and with people. So it's sort of an exploration of new science. And Growing Our Evolution is basically the most recent book that takes the lessons of that first book and the science in the middle book and looks at how that translates into rethinking our agricultural practices at a global scale. So there's this path that goes through my own intellectual development on this, and where it starts is really with the degraded state of the soil globally. This is one of the reasons I'm so interested in the concept of soil health at the moment, because if we look globally, and we kind of, if you'll pardon the fractured analogy, take the temperature of the world's soils, what we end up with is a map like the one you see up on the screen, which the United Nations put together some 10 or 15 years ago. It was an early attempt to look at the state of the world's soil in terms of soil degradation, which has 2 components, the loss of the soil through erosion and the degradation of organic matter in the soil. And you notice there's an awful lot of yellow and red on that map. Pretty much anywhere where there's a lot of people, there's a lot of yellow or red on the map. The world's agricultural soils have been degraded to the extent that we've basically lost the ability to work about a third of the world's agricultural land over the last 10,000 years already. And a lot of that damage has happened in the last few centuries. But I also like to use this map to point out that you could go into any one of those red zones on the map, the areas that the UN declared had very degraded soil. And you can find farms that are turning around the lesson you would take from this map. So farms like we were looking at earlier, that were turning the formerly tan-colored ridge tops into, 8 inches of rich black earth again. I like this map because I can point out both the global problem with soil, but also make the point that there's people who have been turning it around, some of them who are in this room today. And that's the story that I basically want to tell. So if the first half of this talk is a little depressing, bear with me. I'm going to get to the optimistic optimistic bit at the end. And I like to think of the Growing Our Evolution book as the optimistic sequel to the Dirt book. This is a problem, the problem of soil degradation, that I think we can solve, and we can solve it remarkably fast. But we have to think differently about the soil, think differently about the land to do it. And why is this important to do? Well, because we haven't solved the problem yet. The most recent state of the soil report I can find is the UN Global State of the Soil Assessment from 2015, just a couple of years ago. In the executive summary, they argue that humanity, this collective us on this planet, are losing about 0.3% of our global food production capacity each and every year to ongoing soil loss and degradation. Now, when you think about 0.3%, it's sort of a number that only a geologist could get excited about. It's a small number. It's probably about what we all get on our savings accounts these days. It takes years for that interest to add up at 0.3% a year. But if you think of the next century, not as well over history's horizon, but just as tomorrow morning in the grand human experiment on this planet, that 0.3% really becomes a stark and startling number. Because you translate that into 100 years, and it means that we're on track presently to lose 30%, almost a third, of our global agricultural production capacity if we keep going the way that we're going at a global scale. And if we couple that with what we've already degraded in terms of soil around the world, those numbers start to exceed about half the agricultural production capacity of the planet. That is a troubling trend. Fortunately, I think it's one we can turn around, so I'm not here to preach doom and gloom to you all today, but it will require us to think differently about the land. So the backstory is that this is not a new problem. This is a problem that has actually taken the legs out from under different societies in the past. That's what I wrote about in the Dirt Book, which I started in terms of looking at the problem of soil erosion and its interface with history. And why did I start with soil erosion? Well, I'm the kind of geologist, a geomorphologist, who studies what shapes the surface of the earth. And that's basically erosion. You gotta move rocks and sediment, you gotta move dirt to actually shape the land. And so I've studied erosional processes in their natural form for decades. This is how I've made my living as a professor. And so it was a very natural thing for me to look back through history and go, okay, instead of looking over geologic time, I'm gonna look at the time since the last glaciation, a period of time we know is the Holocene, and look at, well, how has erosion affected human societies? And when you look into that, you basically find that it's not a new idea. People have looked into this before. The idea that soil erosion and degradation played a role in the demise of ancient civilizations. And you can make ties to what happened in Mesopotamia, some of the earliest Western agriculture, Neolithic or Bronze Age Europe, classical Greece, Rome, the southern United States, Easter Island, China, Angkor Wat. The list is actually quite long, where you can connect soil erosion and what happened to societies in different parts of the world. But if you read environmental history textbooks, what you usually find is the explanation for it is that deforestation caused erosion, which undermined a society. And I grew up studying erosion in the Pacific Northwest and in California, in steep land terrain, looking at landsliding, places where if you cut the trees down, you get more erosion, you get landslides, but you don't strip the soil off of whole regions like we know has happened in the ancient world. Why? Because if you cut trees down and you walk away, the trees grow back, and they do so pretty darn fast. You get a brief pulse of erosion. And the conclusion that I came to in researching the Dirt Book was that the culprit behind the erosion that helped take down many ancient civilizations wasn't the axe, it was the plow that followed. I ended up writing a history of farming. This is not what I intended to do, but as I got into the story, the connection between how people treated the land on farms around the world, and in particular with the plow, that became the central organizing principle of the book, because that really was the story behind the degradation of land in different regions. So what was it about the invention of the plow that basically allowed erosion to take such a toll on ancient societies? Well, how many of you have ever walked around a native grassland or native forest below timberline and seen wide expanses of bare earth? It doesn't happen. Nature clothes herself in plants. And that goes all the way back some 450 million years ago to the colonizing of the continents by land plants in the first place. What is it about the plow that affected that? Well, it's very good at turning the soil over. That's the whole point. It makes for exceptional weed control to control the growth, immediate regrowth of things. But it also leaves the surface of the soil bare and vulnerable to erosion by water or wind until the next plants come in, whether they're weeds or a crop. And that essentially affects, whoa. Okay, this is not behaving. We're gonna redo that. I think I stepped on the cable, my fault. Oops, no. Why is that not? There we go. Now, I'll just stand 2 steps back. So basically, the villain, if you will, of the Dirt Book turned out to be the plow. It was not the villain that I was expecting to see, but what is it about soil that set that up? If you think about soil as a civilization's bank account, the way that the natural capital that we draw sustenance from, then if you think about soil the way we all think about our own bank accounts, it actually becomes pretty clear. If you spend money faster than you make it, you're depleting your savings. And I know for a fact that if you do that for long enough, you can drive your savings to zero. In fact, you can repeat that several times in your life if you really try it. And at a societal level, the same thing can be argued about soil. If we're eroding soil faster than we're rebuilding it, then we are in fact running out of it. It just takes decades to centuries or millennia for that process to play through the way that a college student can do with one's savings in her early 20s. So what is it that has happened in ancient civilizations? I'm going to spare you all the stories of all the civilizations that I talk about in the Dirt Book, and I'm going to focus on just a couple. I'm going to pick on ancient Greece for an opener because it's a really good example, and because a geologist and an archaeologist back in the 1980s did the geoarchaeology on southern Greece to try and look at what happened in classical Greece, and they ended up documenting that cycles of erosion and soil formation began in ancient Greece right in the Bronze Age, so a few thousand years before the time of Christ, with the introduction of plow-based agriculture. And what that looked like is that this cross-section here that Tjeerd van Andel and Chris Reynolds, the geologist and the archaeologist who worked on this together, put together, this shows you their reconstruction of the Greek landscape, their landscape in southern Greece, right after deglaciation. So 10,000 years ago, sort of the dawn of agriculture in Mesopotamia, this is what the Greek landscape looked like. Hills that had 1 to 3 feet of soil on them, those vertical lines, an open oak woodland, and then the gray stuff is bedrock underneath, the dark brown stuff is alluvium or river bottom deposits down at the bottom. And so what happened when the plow arrived in this landscape? Well, where do you think people first started farming? Well, it was on the valley bottoms. It was relatively flat, easily worked land, right by water. That allowed the population to grow, and what happened is that over time, cultivation spread up onto the hillsides, the areas outside the valley bottoms. And what happened then is that over the course of centuries, the soil was eroded off of the hillsides, and it ended up being piled up in the valley bottoms. Now, is that a problem? Well, yes, if your population has gotten to the point where you're depending on the hillsides to feed everybody, as well as the valley bottoms, and then you're not able to farm on the hillsides, you're not able to support as many people. And you can still find Bronze Age agricultural implements up on bare, rocky hillsides in southern Greece where you couldn't possibly grow a crop today. So they did a really good job of doing the geology and archaeology, and they did it so much so that they could actually reconstruct the population density in this one valley, in the southern Argolit, this one region, ranging from 6,000 years before, 6,000 years BC over there on the left, to roughly 2,000 over there on the right, about the time that they were writing. And so how many people are in this valley? Each one of those black dots represents an estimated population, and the dashed line is there connecting the dots. This is the figure that really got me writing the Dirt Book, because it has two really interesting characteristics to it. One of which I think is trivial, and that is you see 3 cycles there, a low population at 5,000 years BC or so, rises into the Bronze Age, crashes before classical Greece in the Dark Age, rises in the age of classical Greece, and crashes again, and then rises again today. The 2 aspects of this curve that are worth noting are the fact that with each cycle, the population went up. And I think that's actually a very trivial observation, because we have better technology today than they did in the Bronze Age. We can feed more people on the same amount of land today than they could then. And I hope that there's no one in the room that will argue with me about that one. The second observation was, to me, the more interesting one. Why the periodicity? And why does it seem like those spikes are evenly spaced, with a couple thousand years in between, where you have a run-up and then a crash, a run-up and then a crash, and then another run-up, and of course, what's going to happen in the future on this landscape? I like this example because there's very few places in the world where you've had 3 civilizations occupying the same piece of ground, and for which people have done the archaeology and the geology to put together this story. One was erosion happening, one was soil building. So I started asking myself the question of, is there something in this time scale, 1,000 years plus or minus a few hundred, that we ought to be looking at in terms of our global issue of land degradation? And it turns out, as with so many things in science, when you think you've come up with a brand new, original, cool idea, somebody beat you to the punch. In my case, by several thousand years. Because when you go back and you read the classical philosopher Plato, who was writing in the 3rd, 4th century BC, he actually wrote about the Bronze Age soil erosion event, that first cycle in those 3 cycles in the Greek landscape, when he wrote in one of his dialogues that the rich soft soil has all run away, leaving the land nothing but skin and bone. But in those days, the damage had not taken place. The hills had high crests, the rocky plain of Thelus was covered with rich soil, and the mountains were covered by thick woods, of which there are some traces today. What Plato was looking at and describing were things like an olive tree on a pedestal of soil in the middle of a field where a farmer would always eat their lunch under that tree, would not plow around it, would not knock it down, plow it over. It stood feet above the surrounding plowed fields. And Plato recognized that the tree had not brought the earth up. The field had eroded away, leaving the tree on an island of soil. He looked at the mouths of rivers in Greece and noticed that the rivers that were flowing out of forested areas flowed with clear water and did not have much of a delta. The rivers flowing off of the plowed fields were muddy and had big deposits of sediment extending out into the Mediterranean. Has anyone ever been to the ancient port of Rome, Ostia? It's no longer on the coast. It's miles inland. Do you think they built their chief port to supply food to their capital inland? No, they obviously built it on the coast. The coast is built out, and it built out with the soils from the hills of central Italy that were deposited between the 2nd century BC and the 2nd century AD. I read all about that in the Dirt Book, and I'm going to spare you all the other civilizations I sort of did similar kind of research on to try and pull the story together, and instead I'm going to pick on my home state of Washington, because I find when I travel it's much easier to pick on your home state, and then when I speak in Washington I try and pick on somewhere else. So this basically shows in a single photograph why a geologist like myself will be concerned about the problem of soil erosion. This shows you a winter wheat field in the Palouse region in Washington, so it's eastern Washington. Has wonderful loess soils, but they're very vulnerable to transport by wind or rain. They were deposited by wind, they can be taken away by wind. Parallels with the Dust Bowl here. But all those little channels on there are carved into this landscape by a single rainstorm that happened in the fallow portion of the traditional wheat fallow rotation on this landscape. And those little channels can be erased with a single pass of the plow. They're an agronomic nuisance, but they add up year after year, such that this image shows you a fence line up there in the upper right that surrounds a water cistern on the edge of this farmer's field. That in 1911, the land was up at the level of the fence. And by 1961, when the photograph was taken, this bit of a fence row cliff had developed. And what you can't see very well, you might be able to see this little thin black line, so that if you go to the right of that 1961 label, to the right there's a thin black line that may show up on the projector. It shows up on my screen, but in any case, that is a 1-foot increment on a survey rod. This is about a 5-foot cliff that developed in about 50 years on a field that the only thing that happened was that it was in that annual wheat fallow rotation, and sometimes it would rain at the wrong time of year, and you would erode through those little rills. They added up. This is 5 feet of erosion in 50 years. It's about a foot of erosion in every decade. That's about an inch of soil loss every year. There's nowhere on Earth that soil forms that fast, and I can say that with some authority. The fastest rate of natural soil formation that has been documented in the literature is about 2 millimeters a year. One of my grad students documented that on a hillside on the South Island of New Zealand that was incredibly steep, eroding very fast, but soil building was keeping up with it. Now, I also hope you're sitting there thinking that, you know, Dave, isn't this a pretty extreme example? And yes, of course it is. That's why I use it. It's the most extreme example I could find, frankly. So hopefully you're sitting there thinking, well, how typical is it? Because that's the right question to ask. And that's the question that I was asking myself as well. So let's go from that one field in one corner of a farm in one state and stretch out to a whole region, the American South, the Piedmont of the American Southeast, so the hill country, not the broad coastal plains of the Carolinas, not the spine of the Appalachians, but the hill country in between. And let's look at the magnitude of historical soil loss over that whole region. So that gray noodle that's up on the screen now is how much topsoil has been lost off this area since the advent of colonial agriculture, so the last 200-300 years. And you'll notice most of it's gray, 4 to 10 inches of topsoil loss. Some of it's black, more than 10 inches of topsoil loss. And how big a deal was that in this area? But when you go back and you read the original journals of people who first were starting to farm this land, they had 6 to 12 inches of rich black earth over the orange's subsoil. In other words, we've managed to erode off most of the topsoil, and in some places all the topsoil, like I'll show you in a minute, from a pretty broad region of our country that was one of the original breadbaskets of the American colonies, and we did it in just a few hundred years. With technology that was not all that different than what the Romans and the Greeks did to their landscape. So think what the Greeks could have done with an 800-year run in between those population spikes I was showing you. Think what the Romans could have done with a 1,000-year run in central Italy. It starts to put into perspective the idea that even though year to year topsoil loss may be fairly slow, fairly minor, if you let it run long enough, it can add up to things that can actually impact societies. And the loss of the soil itself is not the only problem with soil degradation. It's not the only thing that was depicted on that UN map that I showed you earlier. This shows you an example of two soils. Hopefully the colors show up well on the screens. The one that is on your right is the soil from a tobacco plantation in North Carolina. So it's in that gray noodle that I just showed you in the southeast. And it looks an awful lot like California beach sand. It's kind of khaki, it's got some crusty salts in it. And that's just basically, it was for an episode of the TV show Nova that they asked me to do something on the history of soil in North America in less than 3 minutes so that it would fit in between commercials or something. And what I figured out was we'll go to the tobacco plantation, take a shovel out, scoop up the soil from a field that had been planted with conventional tobacco for about the last 100 years or so, and then go into the forest right next door and take a scoop out of the soil on what had been a farm but had been abandoned about 100, 120 years ago, long ago enough that it had big diameter trees on it. And you can see the color difference in these soils. One is khaki and one is a lot darker brown. That khaki color stuff that looks like beach sand is actually 10-million-year-old beach sand. It's Miocene-age beach sand. There's a reason it looks like beach sand. That's the parent material for the soil here. The darker stuff, what's the difference? It's organic matter. The forest has basically rebuilt the organic matter and the life in the soil followed, but the color difference, khaki to chocolate, is all about carbon in the soil. It's all organic matter in the soil. These are the same parent materials in the same climate immediately next door to each other. The only difference was how people treated the soil for the last century. And that's not unusual to go from that kind of dark soil to khaki colored soil with the loss of organic matter. In fact, tillage and excessive nitrogen fertilizer use are the best ways to actually degrade soil organic matter that I know of, other than just burning it. And very few soils, if you're outside of the peatlands of my ancestors' native Scotland, it's hard to burn soil. This basically shows you that that problem of loss of soil organic matter was not unique to the American Southeast. If you average across the United States, the soil organic matter content, the soil carbon content of many of the agricultural soils across North America is about half of what they were when they first started being farmed. And if you think about organic matter as the fuel that drives the processes in the soil that manifest as fertility, as we'll get to in a few minutes, then you come to the realization that, wow, we've kind of drawn down the batteries of our agricultural land by about half, and we've done it in just a few centuries. And as I said, this problem is reversible. We will get to the optimistic part, but I'm not quite done with the depressing part. How many of you had coffee this morning? Few of you? Oh no, nearly all of you. In part of writing Growing a Revolution, I went down to Central America, to the heart of coffee country, and went to a particular valley that shall remain nameless, that when you drop into the valley and you see it from the spine of the mountains in Central America, the river is flowing the color of, on the right-hand side of the screen, that orangish color. It's the same as the subsoil. Rivers aren't supposed to flow orange. They're supposed to be clear. So dropped into this valley, first thing I recognized was wrong is the river was the wrong color. You then get into the coffee plantations. That slide on the right, the picture on the right is from one of the conventional coffee plantations in the area. You notice that the soil is red right to the surface. Do you think it was always that way? No. This is an oxisol. It's a tropical soil for an oxidized soil, is short for the name. And that's the subsoil that you see extending right up to the surface. The topsoil is literally gone. It's only been farmed for 100 years, and the topsoil is gone. If you go into the jungle, as I took my driver off to look at, you get a picture on the left-hand side. You'll notice that above my notebook there's about a foot or so of decent soil, of black earth, above that orangish subsoil peeking out in the road cut. That's what the topsoil is supposed to look like there. In just 100 years, they've managed to shed their topsoil off pretty much the entire valley that's been cultivated. The problem of soil loss and soil degradation is one that can actually happen a lot faster than we pay attention to year. Now, in researching dirt, I wanted to do the due diligence to try and ask, okay, well, how fast are the world's soils eroding? How much have they been degraded globally? Because I've shown you a few anecdotal examples in classical Greece, the southern US, that field in eastern Washington. But what about at a global scale? So I went to the library for about 3 weeks, and I got all the data I could find on how fast are the world's farms eroding, how fast are the world's continents eroding, how fast have they been eroding since the evolution of land plants, the long-term geological story, how fast do places erode under native vegetation, and how fast does nature build soils. And I boiled that down to 2 numbers for you. I actually surveyed something like 1,500 academic papers to get the data behind this. If you're interested in that, the reference to the proceedings of the National Academy of Sciences is down there at the bottom. If you're a student and you're wanting to write a term paper on this, don't bother doing 3 weeks in the library. Go steal the Excel spreadsheet that all this data is in. At the back of it, you can write a great term paper on it. But just give me credit, that's the way it works. So how fast is the world's soil eroding from farms around the world? Farms that are what I call conventional farms, farms that use tillage, about 1.5 millimeters a year. That's another one of these slow numbers. Your fingernails grow faster than that. And few of us sit around watching them. But that means that it takes less than about 20 years to erode an inch topsoil, on average, from the world's tilled farms. How fast does nature make soil? Well, about 2% of a millimeter a year is the average rate that I came up with. And that means it takes 1,000 years or so to make an inch of soil. The key thing here is it takes nature 1,000 years to make an inch of soil. I'll show you in a minute that my wife has made soil far faster in her garden. And you notice that the gentleman this morning was talking about making 8 inches of soil, presumably in units of time measured in years or decades, not millennia. This is a problem we can turn around, but we have to basically beat nature at our own soil building game to do it. But I've also given you the numbers so far that you can calculate for yourself the average longevity of an agricultural civilization should you choose to do so. And if you have a notebook and a pen, feel free to check my math. It's basically, if you have that net soil loss of about 1 millimeter a year, and I could argue for up to about 1.5 millimeters, but let's be conservative. If we're shedding 1 millimeter a year of soil off the world's farmlands, we could burn through a 0.5 meter to 1 meter thick soil, which is roughly the range that most upland regions around the planet have, if you consult the UN's Global Soil Database. It would only take 500 to 1,000 years to actually erode that all off. Oh, and that's kind of in the ballpark for what we see in the experience of human civilizations in the past. And to a geologist, if you're within 50%, 1,000 years plus or minus 500, that's really precise. It's a nice thing about dealing with really long stretches of time. So the point is that the order of magnitude of these things are about right for explaining the longevity of agricultural civilizations through the loss of topsoil. Now, was that the only thing that affected societies? No, obviously not. Droughts, wars, all kinds of things that contributed to it. But this may be viewed as sort of the background against which all those other things played out on top of. And if you look around at the average longevity of agricultural civilizations around the world, 1,000 years is a pretty good estimate with some really big and glaring exceptions. Societies like the Nile, Egypt along the Nile, early India along the Indus and Brahmaputra, in Mesopotamia, the Tigris and Euphrates rivers, the rivers of lowland China. These are all areas where agricultural societies have farmed for thousands of years and prospered. Or at least in the case of Egypt, up until they built the Aswan High Dam and shut off the supply of silt that was replenishing their landscape. So, don't those examples totally contradict what I've been arguing? Actually, they make the case. Because if you look at all those long-lived agricultural civilizations, they have one thing in common. They were built on major river floodplains. And what happens on a river floodplain? It floods. Yeah, and what do the floods bring? Well, silt, sand, tires, neighbors' cars, whatever is actually in the flow, right? But they reliably bring stuff eroded from upstream. Floodplains are depositional environment. Well, depositional, they also erode, but it's complicated. Boy, I just see if we can get this to stay in there. So, how thick is a single grain of sand? It's about 1 millimeter or 2. Medium sand's 1 millimeter, coarse sand is 2 millimeters. So if we're losing through tillage-based erosion an average of 1.5 millimeters a year, if you're on a big river floodplain, you can deposit a single grain of sand a year and you completely offset the physical erosion that you would lose from tillage. Herein lies the reason you could actually farm on big river floodplains for thousands of years. They're naturally resilient environments. Nature fixes the problem that the plow causes in those environments. It's when we get into the hillsides, like classical Greece, like in Rome, like in the American Southeast, where nature's not rebuilding soils at the pace that we're eroding them, that's where we get into trouble. So this obviously motivates the question of, can we reverse this pattern? Are we doomed to repeat the experience of ancient civilizations, in which case, well, I mean, obviously I didn't come up with that answer, or I'd be just hiding in my basement with a barrel of scotch waiting for the end. No, I think we can fix this problem. I think we can fix it remarkably fast. And I started learning where we could do that in my wife's garden. Because Anne is a biologist, and she's an avid gardener. And when we bought a place in North Seattle, when I got tenure at the University of Washington, I was finishing up writing the dirt book. Struggling with how to write the last chapter because it was a little depressing. And we noticed that she was starting to turn around this problem in her own yard. When we bought the house, it had a side yard that was just covered by what I like to call an old growth Seattle lawn. It was about 6 inches of tangled roots. We pulled that lawn off to plant her dream garden. There wasn't a single worm there. This is what we saw when we pulled it off. This was not the dream soil that she hoped for. And you might ask why we didn't dig soil pits in the yard. We got the attic inspected, we got the basement inspected, we got the kitchen inspected, we bought the house. We didn't think to dig a soil pit in the yard. And the good news is that Ann didn't think to do it either, so I'm kind of off the hook for not thinking about it. But collectively, we kind of forgot about the soil until it came time to plant, in which case it became, oh no, what do we do? And Ann's enough of a biologist to realize that we had the mineral matter for making fertile soil. What we lacked was the biology. We lacked the life in the soil, we lacked the organic matter. So she took it on herself to embark on what we called her organic matter crusade, to bring as much organic matter as she could back to our yard. And that involved things like the neighbor's oak leaves that we would rake up in the fall and bring to our yard. There's a wonderful stuff called SueDo that's available in Seattle, and yes, you can probably guess where it's from. It's from the Seattle Zoo. It's the composted herbivore turds. It's what we can do for livestock in the city, right? We can get it from the zoo. They have a lottery every year, and so where they give some of it away. If you win the lottery, you can bring any size vehicle and fill it up as much as you'd like and take it away. And the first time Ann entered the lottery, she asked to borrow my truck to go get the stuff. I was like, okay, fine. It turned out to be great fertilizer. Second time she entered the lottery, she won. She entered again, she won. Third time she won. And we started to realize that, maybe you always win the SueDo lottery. It's a wonderful marketing deal, and it's actually great. Seattle gardeners love it. It makes for wonderful stuff. Her organic matter crusade, basically composting and mulching and bringing organic matter back to your yard, turned the stuff in that on the left of the screen into the stuff on the right of the screen. That's the soil we started with and the soil we have today. We started with about 1% organic matter or so. Today, around the yard, we have about 10% carbon. So it's a many-fold increase in the amount of carbon in our soil, and it resulted in a huge boost in fertility. We have a lovely garden. I'm going to spare you the pictures of the garden today. But if we talk to gardening audiences, we've got like 10-foot tall lilies. You can't see the neighbors anymore. It's wonderful. We got tired of watching their kids grow up, and now we have a wall of green in between. What we started to think about, though, is what was it that allowed us to turn that khaki stuff into that dark chocolate stuff and do it in just a little more than a decade, about 12 years between those two samples that I just showed you. And we started, the more we looked at it, we realized that, yeah, we were getting the organic matter and bringing it to the yard, but we were not the ones doing all the work. A lot of the work was being done by what we called the hidden half of nature, microbial world, the world below ground and too small for us to detect with our own senses. By the soil food web. We are adding the compost up there in the upper left, and that stuff gets broken down by organisms in the soil, and essentially, we like to think of them as nature's recyclers, taking the dead organic matter and repurposing it into materials that can be taken up to feed the next generation of plants that grow on the land. So the idea that the bacteria and fungi, the decomposers that are breaking that organic matter down, they in turn get eaten by nematodes and protozoa and microarthropods, who then poop out, if you will, the microbial bodies, and microbes think of them as little fertilizer packets. They're full of nitrogen, they're full of mineral micronutrients. They're basically nutrients that once the microarthropods and the nematodes and protozoa consume them and excrete them, they're actually basically manuring your soil from the inside out. You can think of the microbes as tiny livestock that are manuring the soil on the inside. Things like worms that are mixing physically mixing the organic matter and mineral matter, the microbes, a clump of bacteria up there on the left, fungi up there on the right that are connected to that big thing is a root hair, and the little circles are fungi that have their hyphae sticking out into the root hair. But those things at the top, those microbes, are things that get consumed by slightly larger organisms, like that nematode and the microarthropod at the bottom, and they basically convert all that microbial life into forms that can be taken up by plants, more soluble forms. They're organic wastes, or actually we shouldn't use waste, they're recyclers, it's not waste. They're basically repurposing that life. And when Ann and I started to run across this term exudate that's up there on the screen, we started to basically really shift our thinking in terms of how soil restoration was working. Because as we started looking into how does the microbial life in the soil actually work, we ran into the observation that we were not taught when we took graduate level soil science classes at Berkeley some 20 some odd years ago, that plants will take up to 30 or 40% or more of the material they manufacture through photosynthesis, and they push it out of the roots into the soil. And what are they? And those things are exudates. They're exuding out of their roots. And what are the kind of compounds that they're pushing out of their roots? Well, carbohydrates, sugars, simple and complex, proteins. There was even a paper as we were writing The Hidden Half of Nature that documented plants pushing lipids, fats, out of their roots. What does that sound like? Carbs, proteins, fats. I mean, this is food. Why would plants be pushing food out of their roots and into the soil? It makes no sense on the face of it until you start thinking that, wow, they're actually feeding microbial life in the soil around the roots, because if you look in the zone that's labeled the rhizosphere up there, which is Greek for the zone around the roots of a plant, if you want to find an awful lot of microorganisms in the soil, look around the roots of a plant. It's one of the most densely populated regions on the planet, if you just look in terms of life forms per cubic centimeter. And I won't hazard a guess as to the numbers. So what are plants doing? If they were feeding pests and pathogens, how long do you think that would last as an evolutionary strategy? That's a total dead end. They're feeding organisms that actually provide provide a benefit to the plants, because the plants it's a net energy loss, it's a net energy expenditure to actually feed those organisms. And if you look back at the earliest land plants that we have, fossils of, there are mycorrhizal fungi intertwined with their roots. The deal is that plants are setting a smorgasbord for soil life because they get something in return from that soil life. So how does that work? And I termed this the biological bazaar, because it's a trading system. The plants are capturing energy from the sun, converting it into sugars, which they then convert into other compounds. They push those out of the roots. The microbes eat them. These exudates only make it a millimeter to a centimeter away from a root hair before it gets eaten by something. That's about the thickness of my thumbnail to the length of my thumbnail. This stuff gets consumed shortly after it goes out the roots of a plant, and it's consumed by bacteria in the soil and fungi in the soil. And what are those bacteria and fungi doing with it? Well, what any organism does with stuff they eat. They metabolize it, they use it for their own bodily processes, and then they excrete their waste products or their metabolites, in the more polite parlance. What are some of those microbial metabolites? Well, when Ann and I ran into papers that were documenting that these microbes in the soil are making plant growth promoting hormones out of the sugars that are exuded out of the roots, that the plants then take those hormones back up, the light bulb went off. These kind of partnerships work because plants are feeding the microbes, and the microbes are doing things that actually help the growth and, turns out, the defense of the plants. These are mutually beneficial relationships, symbioses. In effect, partnerships where not so much because they wanted to be nice with each other, but because they both benefit. That's the foundation on which lasting relationships can be developed and maintained over millions of years. So those microbial metabolites are being taken back up by the plants, and they help things like plant nutrition. They help in terms of mineral micronutrient delivery. They help in terms of producing hormones that the plants take up. And the mycorrhizal fungi will actually extend their hyphae out well into the soil in a way that serves as root extensions and bring mineral micronutrients back to the plants in exchange for those sugary exudates. This just shows you an electron micrograph of a close-up of those fungal hyphae essentially prospecting for minerals out in soil grains. You can think of the mycorrhizal fungi as the miners and the truckers that are providing the essential mineral elements to the plants who pay them off in sugars. Because what can't fungi do? They can't photosynthesize. They can't make energy. They have to eat either dead things or things that live things push out into the soil and set the table for them to eat. And there's also relationships between plant defense and the microbial life in the soil. There's examples where insect herbivores will, when they start nibbling on a plant, that plant will push out chemical signals into the soil that feed certain microbes that will then either produce compounds that the plant will take back up that either repel the insect pest or trigger the plant to make a compound that repels that particular insect pest. And think about that for a minute. That's every bit as adapted and specialized as the kind of relationships we all know about in terms of pollinators and flowers in the above ground world that we know of and see. So it's not that big a surprise that these kind of relationships are happening below ground, but they've been in that hidden half of nature that was too small for us to detect with our senses below ground, so we tend to not to pay attention to it. And imagine studying the ecology of microbes. They all look like little blobs. I mean, it's a biochemical language, and we've only had tools to study that for the last few decades. This is kind of brand new areas of inquiry. And what it does is it really casts the way we think about feeding plants into a whole new light. And I define two end members that we like to think about as the fertilizer diet and the soil health diet as two different ways to grow large crops of food. It's no mystery that you can take plants in degraded soil, and by adding enough of the major elements they need to promote growth, that you can grow high yields. This is the experiment of agriculture in the 20th century, when we started adding a lot of fertilizers to the degraded fields of Europe and North America early in the century. Why were they degraded? Oh, going to that in the dirt book, it will, you plow for a century and you burn through your organic matter. But in any case, what happens if you're growing a plant in a degraded soil with a lot of a few major elements that it needs for growth is it doesn't invest so much in its root system. It turns into what Ann and I call couch potato crops. And well, why? Well, because if you're just being spoon-fed everything you need for growth, why would you waste the energy of trying to feed all those microbes, all those free-loading microbes in the soil? What you miss out on are the beneficial microbial metabolites that the microbes are producing and the mineral micronutrients that the microbes were provisioning. Plants grown in a healthy, fertile soil, they're more resistant to disease pests. One of the most repeated experiments in botany is trying to grow plants in sterilized soil versus light-filled soil. The plants grown in sterilized soil always succumb to pests faster than the ones grown in soil that has an awful lot of life in it. And those experiments were first done, I think, in the 19-teens, 1911s or so. So plants grown in healthy, fertile soil with a lot of organic matter invest more in their root system to try and feed the microbes that help break down that organic matter and cycle nutrients, and they get more of the beneficial mineral micronutrients and microbial metabolites. And they get not as much NP and K as if you're adding a whole lot of it, but if you have enough organic matter in the soil, you get enough major elements as well. So this kind of realization and the stuff that came out of watching Ann transform our yard led me to start thinking, well, could you repeat this kind of experiment at farms at scale? Because it's one thing to restore life to an urban lot in Seattle where you have SueDo and you have neighbors who are happy to let you steal their oak leaves without paying them for them, even when their plants are all sickly and their ours are really healthy. You kind of wonder why they weren't paying attention. But I took about 6 months off from my job at the University of Washington a few years back to research growing revolution, and I traveled around the world to visit farmers who had already restored fertility to the land, who had done to their farms what Ann did to our yards. Because I wanted to ask, is this, what's the secret? What were their practices? And were they scalable? Could you do this on fully functional, working, economically profitable farms? And basically what I came up with after visiting people around the world is that these principles of conservation agriculture worked pretty darn well to rebuild soil fertility, soil organic matter. And there's a few additions you can have to this list as we'll get to in a minute or two. But the idea of minimal or no disturbance, no-till planting, I mean, that's essential for cutting down on soil erosion. Maintaining a permanent ground cover, that translates into cover crops between cash crops. The idea you heard earlier of always keeping a living root in the ground, that's another way to express it. And having a diversity of crops in one's rotation, at least 4 or 5 crops in a rotation. Or 4 or 5 crops in a rotation, that would include cover crops. So getting diversity in that line. What's the role of diversity? Well, if you think about these things, what's the role of that first one, minimal disturbance? How long would you stay in your house if once a year somebody pulled the roof off, put a giant metal rod in and stirred up all your stuff? You'd move pretty fast. So there's habitat, soil structure, building that. You can think of the cover crops as a way to put carbon in the ground. Think of that as feeding your microbes. And diversity of crop rotations, think about that. What's the point of diversity? Do you know how dysfunctional an entire city made of geologists would be? We'd spend all our time arguing about rocks and starve. Diversity allows different organisms to play different roles in a complex community. It's a recipe for resilience, and the ecological theory behind that's pretty sound. But those 3 principles, minimal disturbance, cover crops, and diversity, are really the recipe for building organic matter and rebuilding soil fertility. Those general principles, I found, translate from one setting to another, from equatorial Africa to Central America, across North America, but the actual practices farmers used in different regions, they were completely different. Why? Well, they had different technological levels, they had different economies, they were growing different crops, they had different climates. But they'd all figured out how to adapt these general principles to their area. So I'm going to show you 4, take through 4 farmers. This first one is Dwayne Beck. He runs Dakota Lakes Research Farm in South Dakota in conjunction with South Dakota State University. He took me to show his farm and his region where they've adopted, or they've widely adopted no-till cover cropping and complex rotations. They didn't adopt these all at once. They did one after the other, but they've now developed a system that's working pretty well for them where they've reduced their inputs of diesel, fertilizer, and pesticide by more than half. Now, imagine the savings economically by being able to reduce your expenditures for those 3 elements on a farm by half or more. And what did that do to their yields? They actually went up. It wasn't a question of trading off environmental benefit for economic benefit. The things that proved to be better for the environment were also better for the bottom line of the farm, because by rebuilding the health of their soil, they were able to use fewer inputs. They're not organic farmers, they still used inputs of all kinds, but they were using less of them. And these were farms that ranged up to 20,000 acres. These were not small farms. When I left Dwayne's farm, I asked him whether or not the kind of practices he was using could work for subsistence farmers in Africa, so at the other end of the agricultural spectrum. And he said, well, don't ask me that. Go ask this gentleman here, Kofi Boa, who runs the No-Till Center for Research in Kumasi, Ghana. So I flew to West Africa, visited Kofi. Notice his hat, got dirt, get soil. I realized I was going to get along just fine with him without it. Before we even spoke a word, just reading his hat. What he's done is he's taught the people in his native village how to go skip from their traditional slash and burn style of agriculture, which, because they were now farming the same land all the time and they weren't rotating it around the landscape, they were degrading their soil at a frightening pace. He taught them to go straight to no-till with cover crops. They get their diversity in the fields all at once, because this room would probably be about 2 farms with the farmers that he's working with. These are small, hand-operated farms. they get their diversity in by having 6 to 8 crops growing all at the same time in the same fields. They'll have like a poly story. What happened to their erosion rates when they did this? Well, their erosion rate fell by a factor of 20. They kept the soil in the land. What happened to their crop yields? Their corn yields tripled and their cowpea yields doubled. And they did this without any inputs. There's a reason that the Green Revolution did not work for subsistence farmers in the tropics, and that is they didn't have money to buy fertilizers. They didn't have money to buy patented seeds. They don't even have money to buy a plow. This was actually transformational for the economics of the farms in this region, and it worked really well. Third farmer I'll tell you about is David Brandt. So many of you have probably seen him speak or his videos. He was kind enough to give me a tour of his farm near Carroll, Ohio. He grows corn, wheat, and soybeans for the North American commodity markets, but that's not all he grows. He also grows very diverse mixtures of cover crops in between and around his crops. He's modeling his tillage radish there, which he basically refers to as food for his microbes. He plants that to essentially help build up his soil. And notice that that radish is pointing at his neighbor's field. Notice that his neighbor's field is a lot yellower than David's field. His neighbor's fields are some rather sickly soybeans at the time that I visited. But notice the green, the little bits of green in his neighbor's field. Those are glyphosate-resistant weeds. They've been sprayed 3 times that year. You cannot kill them. And that has a big yield drag effect on some of his neighbors. So David walked me through what he thinks the economics of his neighbors are and compare them with his own farm. And his neighbors are doing full tillage, they're using 200 pounds of nitrogen fertilizers an acre, 2.5 quarts of Roundup an acre. Their total costs, $500 an acre, at $4 a bushel, they were losing $100 an acre. 24% of farmers in Iowa that same year lost $100 an acre or more on their corn. They would have been better off planting a single pumpkin, harvesting it at Halloween and selling it for $6 than by working all year. That's crazy. Even an academic geologist will tell you, that's crazy. What David was doing, he's been doing no-till for 44 years. He's been doing cover crops for the last decade or two, and he's been experimenting with gradually getting more and more diversity in his cover crops. He's still growing the same cash crops, but he's getting a lot of diversity in his cover crops. He's not tilling, so he's saving diesel out of the gate. He's using about 1/8 of the nitrogen and about 1/5 of the Roundup. He's not an organic farmer, he's a conventional farmer. But I started teasing him that he was organic-ish because he's not using anywhere near as many of the inputs as his conventional neighbors. And he thought that was funny, and we were good with that. But what was really good is that he's making $400 an acre because of his lower input costs and his higher yield than his neighbors who were doing conventional. What was the trick to David's success? The soil over there on the left, that's the soil that he had the year before I visited. It's a Cardington clay soil. It's a heavy clay soil. The photo on the right was soil off of his neighbor's farm, which was like what David started with back in 1971. So in a few decades, he turned that anemic khaki stuff into that rich black stuff. This is what Ann did to our yard. It was the opposite of that tobacco plantation in North Carolina that I showed you. But this shows you, and David did this on a fully operational, commercial, profitable farm. He didn't have access to SueDo. And I'll also point out that he didn't have access to livestock. The last farmer that I'll share you with is a guy named Gabe Brown, who he has a great new book out called Dirt to Soil. I interviewed him for Growing Revolution, and he was the guy who basically convinced me that livestock can be a tool for soil restoration, for soil building. I was trained to think that livestock damaged the land. But it's not about the livestock, it's about how the people operate the livestock, how people manage the livestock. What Gabe's been doing is he's been experimenting with intensive rotational grazing on his to restore native prairies. What I want to show you is what he's done to his market garden plot where he grows vegetables and other crops, and then he brings his cattle in to terminate cover crops, to graze off cover crops. And he has chickens to eat the things that are in the cow patties that you don't want to get into your cows. He's basically using cattle as self-propelled methane digesters to recycle those cover crops, organic matter, and turn it into things that his plants, his cash crops can take up. This shows you what he's done to the soil on that site. In his right hand, he's holding up there, that black stuff, that's the soil from the field I just showed you. The soil in his left hand, the lighter brown stuff. It's not terrible, it's not khaki like some of the others I show you, but it's lighter brown. That's the soil from his neighbor's organic farm. What's wrong with his neighbor's organic farm? They till a lot more than Gabe does. Gabe doesn't till anymore. In fact, I think he's gone off of all fertilizers and all pesticides at this point. Wasn't quite there when I visited him, but by turning his soil into the stuff in his right hand, he's finding he doesn't need anywhere near as much in the way of inputs. So the bottom line is that what I came away with this tour of farms around the world is that the recipe for reversing this long-term pattern of soil loss and degradation that's plagued society after society can be boiled down to what, 3, 4, 5, 7 words. Ditch the plow, cover up, and grow diversity. No-till, cover crops, and diversity in one's rotation. And when you think about how we have taught agriculture for the last 100 years or so, it's the 180-degree opposite of these principles. We've taught to till a lot, to use a lot of agrochemicals, and to plant 1 or 2 crops, to specialize. Turns out that that was essentially the wrong direction when we think about what it would take to cultivate the beneficial life in the soil, but then to work for us. And you could also add livestock if you want to accelerate the process. I don't view livestock as essential to building soil health. I view it as a really powerful accelerant for being able to rebuild healthy soils faster. Now, you don't have to just take my word for the sort of stories that I've been telling you about the farmers I visited. Jonathan Lundgren and Claire Lacan last year put out a paper looking at the economics of regenerative farming. And what you're basically comparing here is the averages from a series of farms across the American Midwest, conventional farming on the left, regenerative on the right, with revenue and cost per acre. So the height of those bars was the revenue on the 2 farms. The colored parts, you're subtracting the expenses, and you notice is that there was a higher revenue on the regenerative farms and lower expenses. That's why that white bit that's left over, the profit, was higher on the regenerative farms. Now, frankly, to me, after visiting farmers I had, that wasn't a surprise, because that was the story that all these people who had adopted regenerative practices over the last few decades were telling me. But it was nice to see that validated. What surprised me, though, was that Lundgren is an entomologist. His orientation is looking at insects, kind of the way that I look at rocks. And this shows you the number of corn pests, the abundance of corn pests on the fields, the regenerative fields versus the conventional fields. Now, the regenerative fields were not using pesticides. The conventional fields were using pesticides. Why are the fields that were sprayed with pesticides have 10 times as many, well, actually less, 8 times or so, 6 or 8 to 6, 7 times as many pests as the ones who are using pesticides? That, I'm surprised that this study hadn't been done before. And there's good ecological reasons for that. When you spray a broad spectrum pesticide, you're not only killing the pests, you're killing all the things that eat the pests. And if you're planting the same crops over and over, you're setting the table for the pests, and then you're wiping out their competition, and every now and then you'll have a pest breakout. And if what you do is you then spray to kill those pests, you've just reset the table for the next breakout. This should be a wake-up call for how we think about agriculture. So what are the kind of benefits we can get from rebuilding soil health? The most important one in my mind at this point is that it can be more profitable for farmers to farm this way. I think more farmers need to know that. We need to figure out ways to do that in different regions that are profitable. We can produce comparable yields. There could be a yield drag for a couple of years, but in the big picture, we face a problem of how do we feed an 8, 9, 10 billion person planet, and not just do it for the next 20 years, we have to do it for the next 1,000 years if we want to last as a civilization. We're not going to do it the way we farm now. We can use less fossil fuel, less fertilizer, less pesticide use. That can result in increased carbon in the soil, better water retention, and less on and off-site pollution. There's lots of environmental benefits that flow from these, from adopting the practices that rebuild soil health. What I'm advocating is that we need what I call a 5th agricultural revolution. We need a revolution in thinking about the soil through the lens of soil health as the foundation for new suites of farming practices. And we tend to get hung up on the question of organic versus conventional. I know I certainly was for many years. But I've become much more convinced now that the right way to think about these issues is through the lens of soil health. And that some of these organic-ish farmers that still will occasionally use pesticide, still occasionally use an herbicide, they're rebuilding the health and fertility of their land. And they're actually surpassing the health and fertility of some of their organic neighbors who still plow too much. I think these soil health building principles can offer advances for both the organic and conventional communities. And there's one other element that I'll touch on before I end, and that is why those of us who live in cities don't care about this. And that's because the soil is where our food comes from. And we took advantage of an experiment last year that a farmer in northern Oregon had done, where he planted 2 fields side by side in the same variety of wheat. He's a no-till farmer, and what he was wanting to experiment with was whether by planting cover crops, he could get the same yield as if he did, as if he was using glyphosate as his weed control. So he took 2 experiments of weed control. Second year in, I got him to send me samples of the wheat grown off of those 2 fields. And what this shows you here is what we did is we ground the wheat up, dissolved it in acid, ran it through the mass spec at the University of Washington. And so there's all those mineral elements on the left-hand side. That first row shows you the amount in parts per million of those elements in the cover cropped wheat, and on the right of the conventional wheat, so the glyphosated wheat. The ratios, the thing I want to point out on the right, you'll notice most of those numbers are above 1, except for the cadmium and the nickel. So the cover crop wheat had more micronutrients in it. And look at that big green number, the number for zinc. We had 56% more zinc in the field that had cover crops for 2 years. You can't change the zinc concentration in the soil that fast. What you can change is the life in the soil that will get the zinc out of the soil and into your crop. That you can change fast. The key to rebuilding soil and fertility, and I think to growing nutrient-dense food, and doing it fast, is to cultivate the life in the soil. That's the part we forgot about for most of the 20th century. It also, fortunately, is kind of the easiest thing about the soil to change. You're not going to change the bedrock, you're not going to change the weather that is causing weathering. You can change the life in the soil and you can do it fast. And that's sort of the take-home message of Growing a Revolution, is that we can solve this problem. We can do it remarkably fast. But it's a challenge to get the word out and to get farmers to adopt these practices. And I don't know where I am time-wise. Do I have time for questions, or should I stop? So we're out of time. So we're at lunchtime? All right, I'm not going to be the guy that prevents you from lunch, but I did bring copies of these books. If you want to grab me, I'm going to be here for the next few minutes, and then just after lunch, but I've got to go talk in Iowa tomorrow, so if you want to get one, grab me in the next few minutes.